All right, let's look in a little bit of detail at nucleophilic substitution reactions. So we're normally talking about haloalkanes in nucleophilic substitution reactions, particularly the alkyl bromides and iodides, and to a lesser extent the alkyl chlorides. Alkyl fluorides are normally not very reactive because the carbon-fluorine bond is so strong. So here we've got an example of what we call an SN2 reaction, where a nucleophile attacks a carbon atom, displaces a halide leaving group, goes via this transition state here to give a new product where the nucleophile has replaced this X group. Now, part of the reason why these nucleophilic substitution reactions occur is that the carbon-halogen bond is polarized because the halogens are more electronegative than the carbon they're attached to. And that makes the carbon electrophilic and therefore wants to react with something that has an excess of electrons, which is what a nucleophile is. So substitution reactions are really just simply the substitution of one group on a molecule for another. So there's many different types of substitution reactions, and we're just talking about the nucleophilic substitutions at the moment. So an example of a substitution reaction, a nucleophilic substitution, would be reacting this bromopropane, 1-bromopropane, with sodium iodide in acetone, which is actually a really common reaction in organic labs called the Finkelstein reaction. So the iodide comes in as I- and will displace the bromide to create the alkyl iodide. So let's just draw that. So if we had the iodine, we could draw all of its lone pairs around that structure, and we could draw the iodine coming in like this, taking that carbon and putting the electrons onto that bromine to make Br- as the side product. So the iodide ion replaces the bromine at the carbon. Now, Finkelstein reaction's really useful to us because this is actually an equilibrium. It goes in both directions, but sodium iodide is soluble in acetone, but sodium bromide is not, and so the equilibrium can be shifted over towards the desired product. Here's another example. Let's take a tertiary alkyl chloride and treat it with water under heating conditions. What we get out of this is a tertiary alcohol. We call this a solvolysis because we're doing it where the solvent is also the reagent. So it's in water as the solvent, but water is actually reacting as the reagent as well. So even though this looks very similar to the previous example, the mechanisms are very different. So we can have a variety of nucleophiles. We can have hydroxide, alkoxides, halides, things like cyanide. So all these have negative charges, and we can see why they would be nucleophiles. We would also have molecules with lone pairs of electrons without a charge, so ammonia or amines. We can have water itself acting as a nucleophile, and we get these variety of products here. So we can do a variety of different reactions with nucleophiles to get things like alcohols, ethers, alkyl iodides, nitriles, ammonium salts, and alcohols. So let's have a closer look at the structure of alkyl halides. Carbon halogens have different electronegativities, so carbon halogen bonds are polarized, and the carbon is at the positive end of a dipole. So if it's a carbon chlorine bond, then that is very highly polarized because chlorine is very electronegative, but the carbon chlorine bond is also reasonably strong compared to other like carbon bromine and carbon iodine bonds. Carbon bromine bond is polarized, and the carbon bromine bond is a bit weaker. Carbon iodine bond is not very highly polarized, but the carbon iodine bond is also very weak, and so it's easy to break during nucleophilic substitution reaction. So here we've got some color coding. The chlorine end is coded sort of colored in this reddish color because it's got a partial negative charge, and the carbon here is coloured in sort of a bluish colour to show that it is partially positively charged. And so nucleophiles are going to want to attack that partial positive charge because they're seeking a source of a positive charge. So there's two different major reaction mechanisms for nucleophilic substitutions. There's SN2 and SN1. The SN2 reaction, substitution, nucleophilic bimolecular. The other one is SN1, and it is substitution, nucleophilic unimolecular or monomolecular. And the first one, the bimolecular reaction, the rate of the reaction depends on the concentration of both the nucleophile and the electrophile, the alkyl halide. And so at the transition state, the nucleophile and the substrate are both involved in that transition state. Whereas in the SN1 reaction, the rate determining step involves a transition state where only the leaving group is leaving from the substrate. The nucleophile is not involved at all, and so the nucleophile is not actually involved in the rate of the reaction. So if we look at that first example, substituting this bromide with iodide, the two molecules have to come together to form a new bond and to break an old bond at the transition state. And so that's why we call it a bimolecular reaction. So both molecules are involved in this transition state. And there's simultaneous bond breaking and bond formation. If we look at this in more detail, we can look at the energy profile as we bring that nucleophile here closer and closer to the electrophile. Okay, so if we start here with just the separator species, will be lower in energy, and then we're going to get up in energy as we start to break bonds and form new bonds. So here we've progressed a little bit closer towards the transition state. The hydroxyl group is coming a bit closer to this carbon that is undergoing attack. As it comes closer, you'll notice that the nucleophile attacks from the opposite side of the molecule that it's attacking from the leaving group. So there's a 180-degree arrangement between the nucleophile and the leaving group. And this is what's known as backside attack. So we always, in an SN2 mechanism, have to have backside attack of the nucleophile on the carbon with respect to the leaving group. Okay, so as the nucleophile gets closer to that carbon that's attacking, you notice that the angle between the leaving group and these hydrogens and the other substituents on this carbon, that starts to get smaller. So those groups start to move this way away from the incoming nucleophile as it attacks that position. And we're going higher and higher in energy as we get closer to the transition state. The transition state is going to be the point at which the energy is the maximum along the reaction coordinate. Okay, so we're finally there. We're at the transition state. We've got a fairly equal amount of bond developing between the nucleophile and the carbon, and a fairly equal amount of bonding between the leaving group and that carbon as well. And each of the three substituents on that carbon are now in a planar arrangement. So they're trying to get away from this incoming nucleophile while also not getting too close to this outgoing leaving group. So that's sort of a steric effect. Now, as that nucleophile gets closer and that bond gets smaller and tighter, and this gets weaker, we'll start to see these things go further this way. So these groups will go further towards the leaving group and away from the incoming nucleophile. So that bond to the nucleophile is getting shorter, the bond to the leaving group is getting longer and longer, and these groups have started to move across this way. And finally, when we get to the products, we've managed to get the nucleophile now bonded to that carbon, and these three groups here are now pointing in the opposite direction to what they were before. Before they were over here getting away from that bromide, now they're on this side trying to get away from the OH group. So the molecule's tetrahedral again, but it's undergone what we call an inversion of stereochemistry. And this can be sort of thought of as a bit like an umbrella blowing open in the wind. So it was like this, and it's been pushed open by the nucleophile, and it's inverted into a new tetrahedral arrangement with those groups in the opposite direction. So that inversion of stereochemistry is an absolutely inherent feature of the SN2 mechanism. So one of the most important factors affecting the SN2 reaction is sterics. So small groups that have a halogen attached, like the methyl group, are very unhindered. And so nucleophiles can come in and attack that carbon without any steric hindrance from things attached to that carbon atom. So methyl halides or halomethanes are very reactive in SN2 reactions. Primary alkyl halides are also still quite reactive. We've only got one alkyl group and two small hydrogens attached to that carbon. There's not much steric hindrance. Secondary alkyl halides, we're getting a bit more difficult now to get a nucleophile in there. There's some steric hindrance here. And tertiary alkyl halides are terrible. They're really slow to react under SN2 conditions. In fact, to the extent that they really don't undergo SN2 reactions at all. So we get the steric bulk really slows down reactions when we're going through an SN2 mechanism. Okay, so how do we get reactions of a tertiary alkyl halides or tertiary haloalkanes like this? Well, we go through a different mechanism. We go through an SN1 mechanism. And this has a rate equation that is the rate constant times the concentration of just the haloalkane. So it only relies on substrate concentration, and it doesn't have any reliance on the concentration of the nucleophile. So SN1 stands for substitution nucleophilic unimolecular. And the first step is rate determining. The first step is breaking this carbon-bromine bond, pushing electrons onto that bromide to generate a tertiary, in this case a tertiary carbocation, or some kind of carbocation in general. And then once the carbocation is formed, it gets attacked by the nucleophile from one side or the other to give the products. And so in this case we've got methanol attacking, so it attacks to give these products initially, and then we've got a hydrogen that needs to be removed in a second step over here. So if we assume the formation of this carbocation intermediate is the rate limiting step, and it should be because carbocations are so high in energy, they're difficult to form, then that explains the kinetics. Once you form the carbocation, it reacts with the nucleophile very fast, and it doesn't really matter what the nucleophile is or how much of it there is. The slow step was forming the carbocation in the first place. So the reaction profile for SN1 reactions looks different to the SN2. We now have the starting material starting down here, going up through one transition state and then down to an intermediate carbocation. And that is a high energy species, so it's certainly not as low in energy as the starting materials that we started with. So that's an endothermic process. But then that carbocation, once we form it, it can react through a second transition state with the nucleophile and go down to a new energy minimum, which is the new product that we've formed. Okay, so if we look at that energy profile with the tertiary alkyl bromide reacting with hydroxide, let's have a look at how that occurs. Firstly, we've got the bond between the carbon and the bromine gets longer. There's no nucleophile involved. It gets longer and longer until it's almost broken, and we're going up through this transition state here, where the highest energy species is actually where the bromine is very weakly associated with this, but we haven't gone down to the sort of separated carbocation. So then we go down to this reactive intermediate, the separate carbocation, where we have a positive charge on a central carbon surrounded by other substituents. Now, it's really important that we recognize the stability order of carbocations. So tertiary carbocations are much more stable than secondary. Secondary are more stable than primary, and primary are more stable than methyl. Methyl carbocations and primary carbocations are so unstable we pretty much don't see them within solution phase chemistry. They've only really been observed in the gas phase. So if we look at the structure of carbocations in more detail, we've got a planar arrangement of three substituents around a central carbon, and that carbon has a p orbital that is empty. And that p orbital that's empty means that we've got a 6-valence electron species, so it doesn't satisfy the octet rule, and therefore it's quite unstable. Now, if it's a methyl carbocation, we've just got hydrogen atoms surrounding that central carbon atom. If we compare that to a tertiary carbocation, where we have carbon atoms surrounding that central atom bearing the positive charge, each of those carbon atoms have bonds to hydrogens. These are sigma bonds. And these sigma bonds here, they can actually overlap through space with the p orbital that is empty. And so we get a through space interaction of these sigma bonds. And that is why tertiary carbocations are more stable than secondary and then primary and so on. We've got 3 different carbon groups with these sigma bonds that can overlap through space. So once we've got that tertiary carbocation formed, it can then either go back towards the starting materials or it can capture the nucleophile in the second stage of the reaction. So the nucleophile can come in from either the top or from the bottom. It's equally likely because the carbocation is symmetrical, and so we can get either one of 2 possible products. Now, in many cases, the 2 products will be the same. If we have some substituents here that are identical, then it doesn't matter whether we add from the bottom or the top. But if we have a tertiary carbocation that has 3 different groups, then the top face will lead to one enantiomer of the product, and the bottom face attack will lead to the other enantiomer of the product. And so we could start with a enantiomerically pure, in this case R, haloalkane, and through an SN1 mechanism, generate equal amounts of the S and the R products, which is what we call a racemic mixture. So this is sometimes referred to as scrambling of the stereochemistry to produce a racemic product. Okay, so we have the nucleophile coming in towards that carbocation. We get up through another transition state where that's a fairly long bond. As it gets shorter and that bonding increases, then the bond forms. We get lower and lower in energy until we get to the final product. And once again, just remember that this is all ruled by carbocation stability. Tertiary is more stable than secondary, is more stable than primary. So if we compare the SN2 versus the SN1 reaction, SN2 is a 1-step mechanism. It's bimolecular. The reactivity order is methyl is faster than primary, is faster than secondary, is faster than tertiary. And so over here with these substrates, we get SN2 reactions. SN1 reactions, we have a 2-step mechanism. It's unimolecular, meaning that the rate determining step involves only the substrate, and so the rate equation involves only the concentration of the substrate. And the reactivity order is opposite to the SN2 reaction. So tertiary haloalkanes are more reactive than secondary, are more reactive than primary, and methyl halides do not really undergo the SN1 reaction at all. Okay, so let's just have a look at this with a quick practice question. If we look at these 4 example alkyl halides, I want to be able to predict which one is going to be the fastest in an SN2 reaction. So SN2, we're looking at the nucleophile with a lone pair of electrons and often a negative charge attacking our carbon with its structure like this by a bimolecular reaction, and it's very heavily influenced by the steric hindrance. Okay, so the smaller these R groups are, the faster the reaction will go. So if we look at this substrate here, that carbon has 1, 2, 3 alkyl groups attached to it. One is an ethyl group, and then there's 2 methyl groups. So that's going to be very hindered. And therefore, it's going to be very slow in an SN2 reaction. So that we could label this one as being a tertiary alkyl halide. Now, if we look at the next one along, we've got 1, 2 alkyl groups and 1 hydrogen. So this is a secondary alkyl halide. So it's going to be, let's just call it slow. And then I'll skip down to number 4 here. We've got a carbon atom with 2 hydrogens and 1 carbon substituent. So that would look like hydrogen. Let's do that again. Let's get rid of this. So there's our group there with the bromine. So that's a primary compound, so that'll be quite fast. And then finally, if we look at this last one here, this is a methyl compound, methyl bromide, which is used as a fumigant, gets rid of pests. But methyl bromide is a halomethane, and so it's going to be very fast to react in SN2 reactions, and so that is going to be the most reactive alcohol halide out of this bunch. Okay, so I hope that sort of helped to clear up some of the issues around SN2 versus SN1 reactions. Remember that sterics are really important in SN2 reactions, whereas carbocation stability is really important in SN1 reactions. Okay, thanks for watching.